Math. All right, here's an illustration of how to use the second derivative test to help you graph. And I've already started this work off on this question by beginning the first derivative test. Since we're asked to graph this equation here, I had to find, first of all, the critical values, which I've shown on the board here as my first step. Values that would make the derivative equal to 0 are possible locations of where the graph could have a low point or a high point. With the first derivative test, remember what we're after is we're after the locations of the high points where it peaks up, or the bottoms of the valleys, the minimum points. And these are possible places where the graph could hit rock bottom or hit the very highest point along the way. The next thing, once we find these critical values, is to lay out some intervals that we're going to explore. Again, we already know that at -1, the slope is 0. And we also know that at 0, the slope is 0, and at +1, the slope is 0. The question is, what is the slope like to the left of -1? What's the slope like between -1 and 0, and so on and so forth? What is the slope like in those four places? I gave the analogy earlier today to a student that it's as if you had a string and you cut the string in 3 spots. You would actually create 4 pieces, smaller pieces of string that you're going to try to find out what's happening in each of those, for each of those pieces. So the three critical values give us 4 places to look. And the next thing to do is to name what numbers you're going to try out. Pick a number in each of these intervals and plug those numbers into the slope to find out if the slope's negative or positive. So you can pick numbers like -2 here. -0.5 is a pretty comfortable choice, and +0.5 here. And even +2 would work out just fine there. From there, you want to take these numbers and you're completing the first derivative test. So the sine of f prime is what you're after next. In other words, is the slope positive or negative for each of these x's? When you plug in a -2 into the derivative, you'll end up getting that the slope is negative. The number part's not important. Here we're just after the sign. What's the slope like when we plug in a -0.5? If you do that, you'll find out that the slope is positive. When you plug in a +1/2, you also get a positive slope. And finally, it finishes off with a negative slope when you plug in 2 into the derivative. So the conclusion is that the graph is decreasing, then increasing, then still increasing, and then decreasing. And to determine if you've got a place where it's a minimum or a maximum point, you're looking for when the direction of the graph changes. Here it's changing from decreasing to increasing, which must mean that there's a minimum point there. Here there's no change, so there's no min or max. Between here and here, there's also a change. The graph's rising, and then it's falling, so there must be a maximum point right here. Where is this minimum point? Well, -1 is the in-between part right here, so the minimum point would be at -1, comma, and we just have to locate the y value. And if you plug -1 into the original equation, you'll end up getting that the y value there is -2. For this maximum value, it's going to take on a maximum value when x is equal to 1. Plugging 1 into the original equation would end up giving us +2 as the y value for the maximum. So we've got that information. All we have to do now is gather some information with the second derivative and put them all together. All right, I got rid of the other stuff for now, so we can now do the second derivative test. Now we're on to figuring out information about the curvature of the graph and also the inflection points where the curvature changes. So the second derivative test, just by its name, is finding the second derivative and setting that equal to 0. So we've got the derivative already here. The second derivative is the derivative of the derivative. So you'd use the power rule again and get negative 60 x to the third plus 30 x to the first equals 0. And you can finish that by using greatest common factors. You can factor out a 30x or even a negative 30x from both of these terms, leaving you with 2x squared here and a negative 1 in its place right there. From here, you got to continue to solve this equation. We've got it broken up into two smaller factors here. So what would make the first thing equal to 0 would be a 0. And what would make this piece equal to 0? Well, you can add 1 to both sides. You can do this in your head, or doing it by hand, step by step, is a nice safe way. There's nothing wrong with doing that. You get x squared is equal to 1/2. You square root both sides, and remember to introduce a plus or minus sign, and you get 2 more values for your x here. You get x is equal to plus or minus approximately 0.71. Now we're going to repeat the similar work that we did with on the first derivative test with these values.